In this video, we're going to be talking about factoring the difference of squares. So the difference of two squares means quantity A is being squared, quantity B is being squared, and we have the difference or subtraction between the two. So notice that there's only two terms here. So if we have two terms that we want to factor, we ask ourselves, is it a difference of squares? If it is a difference of squares, then it will factor into A plus B times A minus B, meaning whatever is being squared here and whatever is being squared here, those are the A and B. And this is a formula that you must memorize because there's really no other way to factor a difference of squares other than recognizing that they are a difference of squares. Because what happens is, notice if we work the other way, we started with A plus B times A minus B, and we multiplied it, we'd get A times A would give us the A squared, and A times a negative B would be negative AB, and then B times A is the same thing as A times B, and then B times a negative B would give us negative B squared. So notice that we have like terms in the middle, negative AB, positive AB, that's 0. Hence, we end up with just the A squared minus B squared. So it's really hard to undo this middle part that is now 0. It's gone. It's not there. So we can't undo the factoring like we've been doing with the A times C and has to add up to B, because there is no middle term now. So whenever we have two terms and they're squares and we're taking the difference, we have to remember it factors into A plus B times A minus B. We also call these conjugates, meaning they're the exact same terms, but the sign in the middle is different. One is positive, one is negative. And that's why these middle terms drop out, because one is negative and one is positive. So let's look at an example here. We have W squared minus 49. This is a perfect square, and 49 is a perfect square. You have to get comfortable recognizing your squares, right? So 1 is a square, 4, 9, let's see, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, so on and so forth. You have to get comfortable recognizing these squares. Alright, so we're back to here. This is the same thing as W itself is being squared, right? And 7 is being squared. So W is our A and 7 is our B, because those are the terms that are being squared. So I plug it into my form here. I know I'm going to have two sets of parentheses. One's going to be positive in the middle, one's going to be negative. And then again, it's to find what A is, it's basically the square root of what you started with. So W squared, the square root would just be W. So that's my A. 49, the square root would be 7. So 7. And notice I still have that plus and minus in the middle. And I can always multiply this back out to check myself, right? It needs to get back to where I started. And in this next example here, just like with any factoring problem, we always start with the GCF. If I see a GCF, I need to take it out. So in this case, a 3. So if I divide out that 3, I'm left with x squared minus 9. 27 divided by 3 is 9. Then I look at what's left. This is a perfect square. 9 is a perfect square. And it's a subtraction in between. So it's a difference of squares. So I know I'm going to go into my two parentheses here, and I say what times what would give me x squared? X times x would give me x squared. They're going to be conjugates, so one's going to be positive and one's going to be negative. And then what squared would give me 9? 3 times 3 would give me 9. And so there you go. So again, the way we find our A is we say what would make x squared? X times X would make X squared. What would make 9? 3 times 3 would make 9. Or you could think of it as the square root. Square root of X squared is X. Square root of 9 is 3. And that's where I got these terms from. Go ahead and try all the ones on the right. Also keeping in mind, notice here that the sum of two squares is prime. It's not vectorable. So I didn't do an example of that. But basically, if you have the same thing but a plus in the middle, it is not factorable. And we'll talk a little bit more about that in a minute. Okay, we're back up here at the top on the right-hand side. We always start with the GCF, and I don't see anything in common. So then we evaluate. I have two terms here. I want to see if they're perfect squares. So 81 is a perfect square, J is being squared, and 4 is a perfect square. So I ask myself, what exactly is being squared? So 9 times 9 would give me 81, and J times J would give me J squared. So that's the quantity that's being squared. Over here, I know 2 times 2 would give me 4. So this is my A, and this is my B. So I factor it into my two sets. I know I'll have a 9J times 9J gives me 81J squared. And 2 times 2 gives me 4. And I need a plus and a minus in the middle. It does not matter which one you put first. If I put the minus here or the plus there, it doesn't matter because this is multiplication and multiplication is commutative. Alright, the next example. I have 12x squared minus 3. So these are not perfect squares, but I do notice that there is a GCF of 3. So I'm going to go ahead and factor that 3 out first. 12 divided by 3 would be 4. I still have that x squared. And 3 divided by 3 would be 1. So now these are perfect squares, right? So 4 is a perfect square, x squared, and 1 are all perfect squares. So I ask myself, what would make 4x squared? 2x times 2x would give me 4x squared. And 1 times 1 would give me 1. So I don't forget my GCF. I'm going to have my two sets. And 2x times 2x gives me 4x squared. I could put my minus first if I want. So minus 1 and plus 1 would give me 1. Again, you can always check yourself by multiplying and making sure you get back where you start. The next example here, we have 64p to the 6th minus 4q to the 4th. Again, we always start with our GCF. There's no variables in common, but there is a 4 in common. So if I divide out a 4, I'd be left with 16p to the 6th minus q to the 4th. Right? 64 divided by 4 is 16. 4 divided by 4 is 1. Alright, then I reassess. 16 is a perfect square, and then these p to the 6th and q to the 4th might not look like perfect squares, but they are. Anything with an even exponent is a perfect square. So let's look at that for a second, right? P times p would give me p squared. P squared times p squared. We already know we add those exponents to get p to the 4th. If I did p cubed times p cubed, 3 plus 3 would give me p to the 6th. Do we see a pattern here? If I wanted p to the 4th times p to the 4th, 4 plus 4 would be 8. So these are squares, right? Anything times itself is a square. So anytime I have an even exponent, I just have to divide it by 2 to figure out what that square is. So p to the 8th is the square of p to the 4th squared. So back to this problem. I know that this is a difference of squares now because those are even exponents. I'm not going to forget my GCF. I know I'm going to have a plus b, a minus b. The question is, what are a and b? So again, back to that idea of a square root. Square root of 16 is 4. 4 times 4 would give me 16. And if we look up here, we already know p to the 6th is p cubed times p cubed. Or, again, I could just take that 6, divide it by 2, and that's how I know this is going to be a 3. And then we need our plus and minus for our conjugate. And q to the 4th, take 4 divided by 2, so I know it's going to be q squared times q squared. And that's as far as we can go. Alright, let's look at another one here. I have y squared and 1/25. So you might think a fraction is not a perfect square, but the numerator and denominator here are both perfect squares. 1 times 1, 5 times 5. So this is still a difference of squares. There's no GCF now, so I go directly into my, here wait, let me get a different color. Directly into my sets, my 2 sets of parentheses. I say, what's the square root of y squared? That's y. Y times y gives me y squared. And then I take the square root of the numerator and denominator separately, right? So square root of 1 is 1. Square root of 25 is 5. So it should be 1/5 times 1/5 would give me 1/25, right? And we could check that. 1/5 times 1/5 gives me 1 times 1, 5 times 5. And then, of course, I need my minus and my plus in the middle for the conjugate. The order of those two does not matter. And here we are with this last one. So the last one is y squared plus 9. Y squared is a perfect square. 9 is a perfect square. But the middle is a sum. It's not a difference. So this is actually prime. It's not factorable. There's nothing I can do with that. And you might wonder why. So let's look at some examples of what it might be. Well, we already know if I did y plus 3 and y minus 3, those conjugates are going to multiply to give us a difference of squares. So that's got a minus in the middle, so that can't be it. If I did y plus 3 times y plus 3, well, y times y is y squared. 3 times y and then 3 times y would give me 6y. And then 3 times 3 is a positive 9. So notice that we'd have to do 3 times y here for the inner, 3 times y here for the outer. That's where I got the 6y. And then 3 times 3 was the 9. Well, that doesn't work because I've got this middle term here that I don't want. I just want it to be y squared and 9. I don't want any 6y. Well, what if I did two negatives? Y minus 3 times y minus 3. It's going to be the same idea. Y times y gives me y squared. Then I could do a negative 3y times y is negative 3y. And then a negative 3y times y. So the inner and outer add up to negative 6y. And then the negative 3 times negative 3 gives us a positive 9. So there's no way, we've done every combination there is, right? One's positive, one's negative. Both positive, both negative. There's no way to drop out the middle term and keep this positive. So that's why it's prime. There's nothing that I could multiply together to get me here. Alright, I hope that helps.